Hello, good afternoon, good evening, or good morning, wherever you might be catching us. I am just happy that you are here for another amazing episode of the Richard Watkins Podcast. I'm pretty sure that today's episode is the latest and greatest. So I'm just happy that you're here today to join us for this amazing conversation. But first things first, we have to give a huge shout out to the folks that make this podcast possible. SPAN, or the Science Policy Action Network. The world is changing. Innovation is coming at you at breakneck speed. Listen, I know if you're like me, which way is up? If you're a policymaker, if you're running a company, if you're just somebody in the community and you're trying to make heads and tails of innovation, education, or health, check out the Science Policy Action Network. They've got folks that can help you out, making sure that you're ready today for tomorrow. That website is span-inc.org. Again, that's span-inc.org. Without further ado, joining us today is Dr. Kari Debbink, a virologist, educator, and leader in public health. Dr. Debbink serves as an associate teaching professor and director of graduate studies in the Department of Molecular Biology and Immunology at the Johns Hopkins Bloomberg School of Public Health, with a PhD in microbiology and immunology from the University of North Carolina at Chapel Hill, and a background in both bench science and science education. She brings a unique perspective to the intersection of research, teaching, and public health. Her work has focused on viral evolution, studying how viruses like norovirus, influenza adapt, spread, and interact with the human immune system. She's also a nationally recognized voice in science education, known for championing active learning and mentoring future scientists. Today's conversation will explore her journey through academia, public misconceptions about virus, and what it really takes to prepare the next generation of leaders in science and health. Hopefully, I did a good job. Welcome to the show, Dr. Devank.
Thank you, Richard. Thank you.
Did I
Good
leave
to
anything
be here.
out? How have you been?
I'm good. I'm good.
Awesome, awesome, awesome. All right. So first things first, first things first. I just read through a bio. I personally am really excited and proud of the bios that I put together. I put on like my reading narration, or narrator voice for this. Hopefully I did a good job. But what did I leave out? How did Kari become Dr. Debbink?
Oh, you left out my pre-PhD jobs and like career, which was teaching middle school.
Let me hear all about it. Yeah, what was it about teaching middle school? And how is that so, like, all right, let's back all the way up, right? So I did leave out a lot. Let's go there. You taught middle school and now you're at Johns Hopkins. Those jobs are identical, different. How did that work prepare you for what you do now?
Yeah, I mean, of course they're different, but they're also very similar. So I'll back up. So growing up, like I loved science. I think you were kind of the same. You were a science person too. Growing up, I wanted to be a marine biologist. That was the goal. Um, but when I got to college, I had like a lot more exposure to different types of science besides just, basic biology. And what I found was that there wasn't really any one area of biology that like really pulled me one way or another. But what I did know is that I loved working with people and with kids. And so I thought, hey, like being a science teacher seems like the perfect type of job for me because I love working with kids. I love mentoring. I love science. I kind of put it all together. Um, and so by the time I graduated from college with a biology degree, I was very set on teaching middle school. And kind of oddly, I mean, maybe this is like kind of an odd way to come to it, but I, because people kind of think of like middle school as like the age that you don't want to teach. But when I was in high school and college, I was a lifeguard. And my favorite age kids that I would like kind of look after at the pool were middle school students because they were funny and they kind of like thought that they were funny in different ways, but you could also kind of fool them and trick them and like mess with them a little bit. And so but they don't take themselves too seriously. So I don't know, it's just like it's a fun age, I think. So um So yeah, so I got my first teaching job like right out of college. And I didn't have an education degree at that point. I basically just kind of like, got hired into a biology, into school, like teaching biology at, shout out to Sarasota School of Arts and Sciences. And that was a really fun school to work at. I had a lot of freedom. Basically, when I first got there, I think it's grown a lot now and they have a lot more resources. But when I was there, they had like one set of classroom textbooks, and like so kids weren't assigned like books or anything. It was just like one set in the classroom. And so I really got to design like the whole curriculum like around, of course, the state standards, but no one was telling me what to do. It was kind of like as long as I did this stuff, you know, great. Like as long as I taught them certain concepts, I could do whatever. And so I got really creative. And it was a lot of fun. And so I taught there for 2 years, and then my husband got a job, my husband went to a PhD program out at University of Arizona. And so when I moved out there, I got a job at a Montessori school teaching middle school, which most people don't usually think of, um, middle school being at Montessori being at the middle school level. Usually you think of it as like little kids. But yeah, Hermosa Montessori School out in Tucson. And I worked there for 6 years, I think 6 or 7 years. Um, and in that time, I got my master's in education. And again, Montessori education is a little bit different than like a traditional classroom. And so a lot of it, the focus is very much on learning and not grades. Um, and that's something that I've really carried with me kind of throughout my educational journey is, obviously sometimes you have to focus on grades because that's what gets you like in the next door. But grades are really supposed to be a marker for how much you've learned and how much you know. And so really at the core, that's what's important. And so I think that's kind of the thread that I've taken to where I am now. And so even at a master's level, at Hopkins, you have students who are very grades focused. They've always done well in school. A lot of them are trying to get into PhD or med school or other professional schools. And so they're still focused on grades. But what I'm trying to do here is, get them to focus on the learning piece, that it's really if you are able to think about science and think about the things that you're learning, that's what people value. And that's what the next step of education values. So when
Wait,
I
can
was,
I jump in really quick?
yeah,
Just really,
yeah,
really quick. My, my
yeah.
my apologies. So it's just really interesting. So you've been able to touch on education in a wide variety of levels and in different spaces and in different theologies of how education should take place. You brought up Montessori just a minute ago. It's throughout your experiences, have you started developing concepts that are maybe independent of the institutions that you work at for what makes a good scientist, right? Like you're putting together all of these pieces so that folks can be successful in life in a lot of different capacities. But if I were to ask you from an educational standpoint, what is important to create good scientists? And I guess one more thing, what even is a good scientist?
Oh man, like Richard, I feel like that's like a really big question. What is a good
It
scientist?
just popped in my head. I was like, wait, she's done so much in educational space, and now she's like really focused on like, how do these experiences, how have they influenced the way you view these things? And what are some of your own personal slash professional theories on education and the scientist? If that
Yeah,
makes sense.
no, it makes sense. So I mean, I think first and foremost, you know, you did a PhD, I did a PhD. A big part of graduate education is developing independence, right? And in developing independence of thought and like how to figure things out on your own and how to troubleshoot, how to know when you know and what you don't know, and then how to find the answers or seek the help that you need to kind of fill in the gaps that you don't know. So I don't know that I have an answer to like what makes a good scientist. Like overall, there's probably not one thing that does that, but I think a big piece of it is your ability to solve problems and be flexible and figure out again what you know and don't know and don't and being open to getting feedback and thinking, like considering new ideas and considering different aspects that maybe you haven't thought of. Another thing I think is like being able to integrate knowledge from different places. So I think especially like when you're in like middle school and high school, everything is divided into courses, and you think of each subject as separate from everything else. But I think as you go through educational spaces, and especially like in, college, in master's programs, PhD programs, the idea is that hopefully you start to see how those things are interconnected, and how, immunology isn't separate from virology, isn't separate from, statistics, isn't, that all these things are really necessary to do good science. And, you can sit, as a virologist, I can sit in an immunology talk or a bacteriology talk, and I can take pieces of things that I know from my specialty, and I can see like, oh, like that's interesting. Like that's an idea that could be similar in my system, So I think it's something that you can't necessarily like, I don't know, directly teach somebody like this is how you do it, but it's a process of learning as you go. And in talking to the master's students currently that I work with, one of the things that we have them do is do a self-reflection as part of their comprehensive exam at the end of the first year. And one of the things that I really noticed in the answers that was very consistent was this idea that prior to coming to the program and prior to like going through the coursework and being in the lab, they thought of science as very black and white, or they thought of reading papers as very black and white. They read a paper, whatever the paper says is true, right? And then you kind of learn how to think critically about information, and you learn more about how, things are done, and like caveats to like doing like a type of experiment, or caveats to this information, or, whatever you're working with, right? And so then you can kind of have like more insight into seeing that it's not always black and white, that there's gray areas. Like you can have a great study that gives you X result, but the caveat is that this was in this population under these conditions, or, and so I just think like, being a good scientist is really about putting in the time and the effort into like getting to that point where you start to see the caveats and you start to see how things are fitting together. And that's not to say that you can't be good in certain ways like prior to that. I think, you have these great undergraduate researchers that are young, enthusiastic about science. They're doing great research too. It's not to say anything. It's just that, you do grow as you go, and it's not till you get to the next level that you saw like, oh, like all these things that I've been doing have helped me get to this new level of understanding and ability. I don't know if that really answered your question, but
That absolutely answers my question. But another thing that pops in my head, again, everyone, if you're just jumping in, Dr. Kari Debbink, Johns Hopkins, Bloomberg School of Public Health, is that concept of public, right? It is in your title. You've gone from the bench, right, into a space where you're always going to have to consider the public, especially when you're talking about public health, right? Consider the public. As a scientist, what do you think the public thinks about science? Like that's a huge question, but it's got to be one that individuals in public health think about, because the public are, the end of the line user of the innovations and the services that the talent that you help create, right? Those are the ultimate, recipients of those, services. So when we kind of think about that, what are you thinking about when you think about the public, when you think about folks that aren't necessarily coming into your building to grow? What are you thinking about the folks who, I guess, your folks and you serve?
yeah, I mean, so obviously the public isn't just one group, right? I mean, the public is just this incredibly diverse, like intersection of all, different experiences across the spectrum, right? So I think that's what sometimes makes it challenging, right? Because everybody is looking at public health from a very different lens. Somebody that's like living in a rural community, um, in Alabama is like very different than somebody that's maybe like living in like New York City. you know, people have different values. People think about it differently. People are exposed to different messaging around public health, and it may even it also depends on like what you're talking about. Like somebody may think completely differently about cancer versus like an infectious disease, and I think we saw that during the COVID-19 pandemic that there were people that were more or less open to hearing messages about what they could do to protect themselves. Like there were people that refused vaccines or refused to mask and that kind of thing. That may have been completely different if you were talking about cancer and cancer treatments, right? Those same people may be very willing to, get whatever the latest cancer treatment is, if unfortunately they become ill. So, I think that's the difficult thing is like, how do you reach the populations that maybe need to hear a certain message? And how do you make them receptive to hearing the message that you're trying to get across about public health?
Do you think the public have a hard time dealing with the concept of virus that they don't necessarily have with something like cancer, right? Does the concept of cancer, is that more of a kind of solid crystallized idea in folks' head, whereas the concept of virus is more nebulous, harder for folks to get their hands around? I don't know if that's true, but do you think that's true, or do you think they're both looked at in the exact same light?
I definitely don't think they're looked at in the exact same light. And I think the reason for that is that people have experience with both cancer and with viruses, but they tend to be very different experiences, right? So people tend to think about cancer as something that can kill you. And so if you don't fix it, it kills you. Whereas with viruses, I think people haven't seen as much death from virus. Like, sure, we had COVID-19 and like people, and there were a lot of people that died from that. But in general, most people's experiences with viruses are things like colds or, seasonal flu or, things where they get sick, they're sick for like a week, 2 weeks, and they recover, right? Um, and that's I think a lot of what people think about viruses. And even though we know as virology people that viruses like kill a lot of people, the average virus doesn't kill somebody, right? And so that's just people think of like cancer as more serious than viruses. I think it shifts a little bit when you get into something like HIV, which you studied as a PhD student. I think people do think of HIV as in the same ways that they think about cancer in a lot of ways, because they think of HIV as like something that kills you. They think of
Wait,
cancer.
why do you think why do you think HIV, and I think you've already touched on it, and I think I've heard the answer already, but I'm just going to ask it again, so please forgive me. But why do you think HIV is looked at differently than something like SARS-CoV-2, the virus that causes COVID?
Yeah, I think because it was something that wasn't even known about until the 80s, really. So, if you think about like we were kids, right? And our parents, like they were the ones that were like young adults, like when HIV was identified and characterized, right? And so I think, those first couple decades where we knew about HIV and what it was doing, um, most people died, right? And I think there's still that like stigma that goes along with HIV that's not necessarily there with other viruses. As we know, like as virologists, HIV drugs have come a long way, right? So like HIV is no longer a death sentence. People can lead very normal lives, you know, being HIV positive with the current drugs that we have. But it wasn't like that, in the 80s and 90s. And so I think people still have that fear um, from that time.
So it's that kind of, for lack of a better word, it's that type of kind of like death sentence feel when, all right, it's cancer, or all right, I'm positive for HIV. It's that kind of a feel of like, oh my gosh, let me get my affairs in order. Whereas with the virus that causes COVID, even though it killed a lot of people, if you found out that you had COVID, it was not that same experience as if somebody told you you have cancer, or somebody told you that you tested positive for HIV. And thinking about pandemics, because I have always been just absolutely enamored with pandemics, and that might come from a place of fear, quite honestly, right? Just enamored with pandemics. Um, I grew up. I think the actor's name is Dustin Hoffman, I think, and Cuba Gooding Jr. in the movie Outbreak, where they were dealing with the Mutaba virus, right? I think that was supposed to be like a fictional kind of like Ebola, airborne Ebola kind of thing. But then you've got, Matt Damon, Gwyneth Paltrow in Contagion. And then, quite honestly, movies like Rise of the Planet of the Apes, or what's the movie? What's the movie with Will Smith? I Am Legend, right? Which kind of touch on, pandemics. This might sound silly, but do you ever think about that? Like, were these movies influential in the way you view, like I'm part of that? You watch those movies, you're like, what would I do in that situation? How would I, one, how would I kind of keep my family safe? Or two, what then is my responsibility to the public, right? You've got public health all behind you. So let's go there. One, do you think you can give folks your definition of a pandemic? And two, if you were a character in one of these movies, how would you act? And I'm going to save my third question for later. I don't want to put too much on your plate. And there's no such thing as a wrong answer. I actually,
There
bad
probably
answers.
is, but
No, there is. But yeah, what's the influence of, movies like that on the public's perception of what a pandemic is? And break that down for us. What is a pandemic?
yeah, I mean, first of all, I think those movies make it seem like any pandemic is like deadly and is going to kill like a huge part of the population. And really a pandemic is a disease that spreads, globally, basically, right? I mean, it's something, and that could be anything from the annual flu, like flu that circulates every once in a while. We have a pandemic, or we consider it like it's a flu strain that infects more people than other flu strains do, right? Sometimes we have, other viruses that cause a pandemic, and it doesn't necessarily mean, again, that it's like deadly. It just means that it spreads very widely, right? Um, I think, yeah. I mean, obviously, those movies, it wouldn't make like an interesting movie if it was like there's a cold pandemic and everybody got sick for 2 weeks. Like, right? That's not a movie, right?
It would be good though, but I don't know if you could cast Cuba Gooding Jr. Also, a tangent, please forgive me, but for the folks to laugh, I consistently I don't want to say confused, but even in professional settings, I don't care how serious the moment is. Um, Routinely people raise their hand and they'll say, "Hey, has anybody told you that you look like Cuba Gooding Jr.?" So don't laugh too hard, Kari. It's not that funny.
I can see it. I can see it.
All right, so yeah, it's yeah, the chicken pox, or what did you say, the common cold, which is caused by a wide variety of things. If you're thinking about a virus out there, all the viruses out there, H5N1, flu, HIV, Ebola, coronaviruses, what virus are you like most worried about? I don't know. I don't even know if that's the best way to ask it. What virus are you like? This one, this one is going to be the bad one, or I'm worried that this one's, or is it a virus that we just ha- currently we don't have, but will newly emerge? Yeah, what virus do you have your eye out for?
Yeah, I mean, I think I'm scared of a flu virus. I'm scared of some of the flu viruses that have not like spread officially into humans, like H5N1. There's a couple other H types that haven't been in humans, but haven't spread widely in humans, but have infected like people working with livestock or working with, poultry, or, so those are the ones that I'm concerned about, that I have, that kind of would make the most sense to me to emerge. I mean, I think another coronavirus is possible. I think we have better tools now to address coronavirus vaccines. But I think that still poses a threat. Um, for me, like those are probably the most likely ones, like the respiratory viruses.
No, I completely agree. I remember on my interview weekend before graduate school, it was just, I wasn't even a graduate student, just interviewing. I just remember saying that, yeah, I'm really worried about influenza. It's a tricky little thing, right? Got the segmented genome, right? You've got opportunities to change through shift and through genetic drift as well. Um, what okay, let's back up. So you said the flu, right? Tell me, and keep in mind, the folks that are going to watch this, some of them are going to know what H and N mean when you say H5N1, hemagglutinin or neuraminidase, right? Some folks are going to know exactly.
I'll try not to use those words.
No, some folks are going to know automatically what that means, but there are going to be a lot of folks out there, right? Maybe, your cousins or somebody's going to chime in that might not know any of these things. Tell us a little bit about kind of the tricky nature of influenza, right? It's not just a problem in people. It's also a problem in other animals. Break that down a little bit for us, for the folks who might be hearing this stuff for the first time.
Yeah, so influenza is a really interesting virus. I mean, of course, as a virologist, I'm going to say most viruses have something interesting, but influenza, like Richard said, it's kind of cool because it has what's called a segmented genome, and so like most like most things have or most viruses like have their DNA or their RNA kind of in one piece, whereas influenza has like many different pieces. And each of those pieces has a part of the genome, has a protein. And so I'm sure like most people like with seasonal influenza, they've heard of like H3N2 or H1N1. Though those numbers, the H is referring to a part of the virus that's on the surface, and the N as well. And so basically what happens is like the H is on one piece, the N is on another piece, and then there's some other genes, but we're gonna forget about those because it's not important to what we're talking about in this term. So you have like all these different H's, and like there's around 18 different H's. There may be there may be a couple more that people are wondering, that maybe have on the horizon or whatever, but there's about 18 different H's. I don't remember how many N's there are at this point, 9, 11, something like that. Anyway, so out in the world, there are like these 18 H's and a bunch of these N's, right? And because they're on these individual like pieces of DNA, what happens is if a virus with, let's say, an H3 and another virus with an H1, they infect the same animal, they can swap all their genes around. And so now you can have, the H mixed with another N, from a different virus. And so you can end up with like new characteristics based on those swapping of different genes. And so if you think about influenza kind of globally, like we have like H5N1, we have H1N1, we have H3N2. Historically, we've had H2N2 as like viruses that have infected humans and caused, pandemics throughout history, right? But then there's all those other H's, right? So we have 1, 2, and 3, but we haven't had major spread of any other H type into the human population. We're seeing a little bit with H5, H7, H9. There's been some other variations that have gotten into humans in very limited basis, but haven't really spread efficiently between people, right? So it's just like a pinging of, I work with, poultry, and it transmitted from a bird to me and I got sick, but I didn't transmit it, right? So the danger is that our immunity in our vaccines are covering those seasonal influenza strains, your H3s and your H1s, right? And it's not really getting to any of those other 18 different H types. And so the reason why virologists are really concerned about something like H5N1 is because if an H5N1 virus gets into the human population and then is efficient at getting from person to person, the transmission rate goes really high. We don't have protective immunity against that. And it could be that it ends up not being a very pathogenic virus, but the turn is that it also could end up being very pathogenic, and we just don't know, and we won't know until it gets in and spreads, right? And so, if we think about the H1N1 pandemic, the 1918 flu, right? It killed a lot of people. The mortality rate was very high. And so the concern would be that we would have something similar to that, where you would have uncontrolled spread, basically, of a virus that there is no population-wide protection against. And then it could be something that would end up killing a lot of people. So, that's why I think it's concerning that, we have this H5N1 outbreak that's, in birds, right? And has now gone into cows and some other livestock animals. And so the concern is that it's kind of spread into new animals, and like, what mutations does it need to then spread efficiently between humans, because it's also infected humans, but it hasn't yet spread efficiently. And so that's the question. That's why flu worries me.
Yeah, no, I love that. But I realize that I think we did. Yes, I'm pretty sure we did. We put the cart in front of the horse.
Oh.
And this is my fault. This is all my fault. And by the way, I just want to also point out that I hate the terminology, you put the cart in front of the horse, because that horse can still push the cart. I mean, conceivably, it doesn't have to be a horse-drawn carriage. It can be a horse-shoved carriage. So anyway,
Not as efficient, not as efficient.
not as efficient, right? It doesn't even know where it's going. All right, here we go. What's a virus? I know that's what I meant when I said we put the cart in front of the horse. What is a virus? Do you know that a lot of folks are, don't really know what a virus is? What's the difference between a germ and a virus, or germ and a bacterium? I'm sorry. You're going to have to become fields virology to all of our audience. To the best of your ability, what is a virus?
Yeah, so I mean, you just use the word germ, right? And that's kind of like the big pocket of like everything that causes disease, right? That's your big pocket of everything that causes disease. And then within what people would say germs, like, and that's, like a colloquial phrase, right? There could be different things. There could be bacteria, viruses, like maybe you throw in some fungi, maybe you consider parasites germs, I don't know. But so there's like these like little categories like within what you would consider like a pathogen or a germ, right? Viruses are the only ones that are not cellular. So bacteria are single cells, parasites, are cellular organisms, fungi, cellular organisms, but these viruses are kind of weird in that they can replicate within a human cell or whatever organism they infect, so like, right? But they can't do it by themselves. So they bring in pieces of what they need to make more of themselves, but they don't have everything, right? So generally, if I'm just speaking very generally about what a virus is, it's got some type of DNA or RNA, and then it's surrounded by some type of protein coat. Sometimes they have envelopes, sometimes they have other proteins, sometimes they're really complex and do weird things, but at the base, it's basically like this protein coat with some DNA or RNA in there, and then it infects cells, and it uses the cell's machinery to basically make more virus. They burst out of the cell, infect more cells, and on, right?
I always think that's just absolutely just crazy to really kind of think about. No matter how many times I hear what a virus is, it still blows my mind. It is like the laziest thing on earth, right? It doesn't do, I mean, listen, it's like inviting somebody over your house and they're supposed to cook dinner, but then they come empty-handed. They didn't have any of the ingredients. Right. And so they'll need everything in your house. And by the time they leave, somehow it's more of them. And then you don't have anything in your house and somehow it burned down. Right. Because it takes all of your machinery. Right. You can't even do your own stuff because this freeloading virus is just using up all of the Wi-Fi, all of the electricity, all of the water. It's just,
Yeah,
I'm,
and then half the
they,
time it does, it like kills you on the way out, right?
right. Or viruses are kind of weird. I suspect that they don't even want to make us sick. I suspect they don't even want to kill us. I think a virus is content replicating in peace, its host unaware of its presence, and then its host goes around other potential hosts and coughs on them. Like that is the sweet spot for a virus where it can spread without people dying or making themselves sick. So that is a really, really great understanding of viruses. So what do we do to kind of deal with viruses, right? So you mentioned the Spanish flu that started in Kansas. I think I said that right. 1918. Spanish flu that started in Kansas. Um, but then we didn't even know what viruses were like back then. But since then we've learned a lot. If you were determined to have a virus, any virus, what then do folks do, right? So what do you do to get better? How do you treat something with a virus?
Depends on the virus, right? I mean, the best thing to do is actually prevent a virus because it's much easier to prevent it than it is to actually treat it. Obviously, we do have antivirals for a lot of different viruses, but there's many viruses that we don't have antivirals for. So for a lot of them, it's like treat the symptoms, like make sure the person is hydrated, make sure that you're controlling whatever the symptoms are. Um, Really, like I said, prevention is the best thing. So it's like things like if there's a vaccine, vaccinate. If it's, oh, there you go, sneezing, spreading your virus all around.
Hey, we're on speaker mode, so folks
Oh,
didn't even know I
okay.
sneezed.
Well, so for those of you that can't see Richard, he just sneezed. He just sneezed.
I know. I'm so
Off
sorry.
camera. That's okay. Anyway, um, masking if you're sick, washing hands, because again, different viruses are going to spread in different ways, right? Like, so if you have a sexually transmitted virus, it's wearing protection like when you're having sex, right? If you're talking about a respiratory virus, wearing a mask.
How does norovirus
Oh
spread?
yeah,
That's
norovirus, like that's my favorite virus, right? That's what I worked on for my PhD work. So norovirus, for those that don't know, is basically, what people call like the stomach flu. It's not actually flu, it's actually norovirus. So causes vomiting, causes diarrhea. It's the thing that you feel like you're dying for like 2 days and then you get better. But to prevent norovirus, like this is a virus that has a very low infectious dose, so not very many particles like make you sick, right? You basically get it by ingesting small amounts of virus. So like what we're talking about there is fecal or contamination,
There we
right?
go. That's what I wanted to hear. People eat poop and then they get sick. That's what we're going for.
It's true. With norovirus, like if you're getting sick, it's because you're eating either poop or puke, basically.
Well,
Um,
hold on. Can we ask a question here? So it's very easy. Like I would imagine. So I work. There's a lot of offices nearby, and if somebody were to walk by and you were like, "Hey, you get this from eating poop," that person would be justified in thinking like, "You got to be an idiot to eat poop." But like, it's not that simple. People aren't consciously did you see me?
of course, no one
did you
like
see
no
me
one
just
just
motioning? I was almost about the motion eating poop. I'm glad that I didn't finish that. But it's not that simple. How do people come into contact if something is transmitted, as you were saying, through the fecal oral route? This is crazy. Go ahead.
Yeah. Of course, like nobody like means to eat any like fecal particles. Like I think we all know that. No one's doing that on purpose. But what happens is that there are small amounts of fecal contamination all around us, right? Like, in the water, like in, water and food, things like that. So a lot of times you'll get this associated with like outbreaks in restaurants. And it usually happens because either an ingredient had like fecal contamination, like somewhere in the processing, or maybe even from the field. Um, or someone in the restaurant was sick, like a food worker was sick and didn't wash their hands well enough. And if you think about a virus that has a very, very low infectious dose, like less than 20 particles makes you sick, even if you're washing your hands, you could have more than 20 particles. You could probably still have millions of particles or thousands of particles on your hands. And if you're
Particles are sturdy too, right? Am I wrong? But the norovirus the particles are pretty sturdy, right?
Yeah, they're
But
also sturdy.
there we
Yeah.
go. Yeah.
Yeah, so they don't break down easily. So they can persist, for weeks, on surfaces in the environment, that kind of thing. And so, it's very common for there to be enough fecal particles present to make somebody sick. And so a lot of times in a restaurant environment, it's because it's on somebody's hands that was sick. It gets into the food. Like even if you do a decent job of washing, maybe you don't get underneath your fingernails super well, or there's places people miss. Um, oysters. Oysters are, filter feeders, and so um, people get sick from eating raw oysters because those oysters, they like basically filter the water, and they take all the water, and they're filtering it through, and they're trapping some of this virus like in their nice meaty little like muscle inside of them, and then when somebody slurps that raw oyster down, they're getting that fecal contamination that was in the water, and they're eating it directly. And
Even if you put hot sauce on it, the hot sauce doesn't do anything. I'm joking. I'm joking. No, I'm just joking.
Richard, maybe that's a study that somebody should do, like whether hot sauce inactivates norovirus. My guess is no, but I
I
don't
feel
think
like
it's
I couldn't get
bad.
that funded, right? I get that funded, but jokes aside, I hope nobody out there thought I was
No,
serious. No,
no, no,
that hot sauce doesn't do anything. Sorry to cut you off.
no, you're good. You're good. Um, it's also like pretty common in like retirement communities, places like that, really anywhere where people live in close proximity, just because again, it's hardy. It doesn't take very much to make you sick. So you get like one person sick and it's very easy to spread. Even people flushing the toilet, it aerosolizes, settles out on things, other things in the room. And so you touch surfaces. Yeah. So there's just, you know, I don't know how we got on talking about norovirus, but I could talk about this for like an hour. So I'll stop there.
Yeah, no, well, listen, I think I wanted to talk about it because there was an opportunity to talk about poop. And any chance that, two well-educated folks can sit down and have a serious conversation about poop, that's an opportunity that I do not want to let go past. So that's how we
Fair enough.
start.
Fair enough.
But listen, again, we have Dr. Kari Debbink, Johns Hopkins, Bloomberg School of Public Health, who's joining us now. And again, just thank you, thank you, thank you, thank you, thank you for being with us today, but also just thank you for the service that you provide. I've had an opportunity to know you for a while. I've always, viewed you as an extremely prolific researcher, going all the way back to graduate school. Just being able to admire you from afar, even though we were at the same university, I was just like, this person is incredibly prolific and amazing and hardworking. But this is something that I get a chance to say about a lot of my guests. I am honored and privileged to talk to some of the most amazing minds in the entire world. You're in that category, but it's a gift and a curse. The curse is an hour goes by, I feel, faster than the blink of an eye.
Right.
And what happens, I kick myself, and I say this at the end of every episode because without exception, the call ends and I'm like, oh, I should have asked this question. I should have asked that question. Oh, I'm an idiot. Why did I waste time talking about poop? I should have been talking about this. So I wanted to take this opportunity to ask one final question. Is there a question that you hoped that I would have asked that I never got around to? Or was there a topic that you hoped that we would touch on that I never mentioned that you were like looking forward to discussing? We've got a little bit of time left. I want to be mindful and very respectful of your precious time, but I did want to give you an opportunity to let to tell folks like I was thinking that I was going to get a question like this, and then after you say it, please feel free to answer your own question.
Okay. Well, I have two things. All right. So the first thing is I wanted to go back because I never kind of explained how I got from teaching middle school to now, being at Johns Hopkins, right? So while I was teaching middle school, one of the things that I realized was that there were certain topics that I really loved to teach, right? And, like within biology. And if you remember what I said, like when I was in college, there was never anything that like I felt like stood out more than other things. But when I was teaching general biology, I found that I was really drawn to environmental science and genetics and microbiology. And so my husband was doing a PhD at the time that I was, at Hermosa Montessori, teaching Montessori middle school. And I was always around graduate students, and it made me realize that I really missed the process of learning. Like I was teaching people, but I wasn't learning. They were doing all these really cool, like, scientific studies, and it was kind of like, I was missing out, right? And so I did a couple like summer internship, like research internships, like while I was a teacher, um, and applied to, PhD programs. Now, what I'll say is that with the experience that I had, I would never get into a PhD program today. Absolutely not. I did not have enough research experience or enough direction. But at the time, like, UNC Chapel Hill saw something in me, saw something in my application. They accepted me to their PhD program. I absolutely loved graduate school. Loved the people that I was, loved the lab that I was in, loved my cohort, including Richard. Still keep in touch with a lot of people that were in my PhD cohort. And then after that, my goal was always to teach, go back to teaching. I wanted to do research and I wanted to teach. So after my PhD, I did a few postdocs, and then I got my first job as an assistant professor at Bowie State University. And I was there for about 4.5 years. And I really loved teaching like the undergrads. I feel like that's like my sweet spot for teaching is like at the undergrad level. But the um the environment there wasn't like quite right for me. And so when I was given the opportunity to come to Hopkins to like run the graduate programs, like here in this department, I took it. And now I'm like, working with a different level of students, master students. And one of the really interesting things, and you kind of asked me this at the beginning, what's similar, what's different about, the levels, is that students like at every single level from middle school up to like master's and PhD students, there's some like very big commonalities. Like you still have like a subset of people that are, you know, always going to be like on the ball, like doing everything they're supposed to do, like on time. You're always going to have the few that are like, you've told them like 5 times what to do and they still have no idea what to do and they're still asking you the same questions you've answered. Like you still have like the people that, um, are good at procrastinating and can like at the last minute, like pull out something amazing and like submit it. And you have the people that like stress about it and like have to do everything ahead of time. You still have like the same students at like every single level, which I always think is like so interesting. Like people always say like, oh, teaching grad school must be so different than teaching middle school. And in a lot of ways, it absolutely is not. Um, the content is different, right? Like it's more in depth, but it's like you still have the same types of students at every level. Um, yeah, and I think along with that, one of the things that I wanted to say was that, if there's people out there that want to like be scientists or like be in education, be in like different places, there's no one way to do it. Like as you can see, like my career path was like very meandering and windy. Um, but I got into a position that's a really good fit for me. I get to work with students all the time. I get to teach. I'm not doing active research like in the lab anymore at this point, but um, I keep myself busy, plenty busy with all the other things that I have to do with like developing programs and running the programs and teaching the classes and all those kinds of things. And I really love it. Um, and then the second thing that I wanted to say is this is just giving a plug to science, right? I think that, science has really been under attack over the last couple months with, proposed cuts in funding. We are having grants frozen to universities kind of across the board, changes in how we're going to be distributing money from NSF and NIH, cuts to, programs that are, supposed to be saving lives from HIV, like, and in other infectious diseases, like in countries across the world, and in the United States, like we're, seeing cuts to disease preparedness programs. And, one of the things that I just wanted to say is that if you have the opportunity, anyone listening has the opportunity, please speak to your representatives about not cutting funding to these programs, because we live in a global society and things that go on here in the United States impact people across the globe, and things that happen all across the globe impact people here in the United States. Like we are one world. We have the ability to prevent and treat these diseases, a lot of these diseases across the board. And really the only thing keeping us back is access is people having access to a lot of these things. And um regardless of what political views people have, like I think at the end of the day, like most people want to save lives. Most people don't want to see people suffering needlessly. And so I think the investment in science is really an investment in everybody currently and in our future as well. And by cutting scientific funding, we're not only, damaging people now, but it's preventing the development of new vaccines, new drugs, new cancer treatments, new Alzheimer's treatments. And those are the things that are going to be helping our generation and the younger generations when they get older. And so, it doesn't make sense. It really makes sense for people to support science and to support making sure that, we have the things that we need to prevent disease and death.
Well said, well said, well said. Dr. Kari Debbink, Johns Hopkins, Bloomberg School of Public Health. Thank you so very much for taking time out of your day to be with us and sharing these very important messages and insights into what viruses are and what pandemics are. And that very final message of supporting science is absolutely critical. Thank you so much for being with us. If you are tuning in, thank you so much for checking us out. Make sure you check out other episodes of the Richard Watkins podcast. You can find them on Facebook, LinkedIn, and YouTube. And signing out, we'll close like we always do by saying that remember, the future is not something to wait for, it's something to build. Thank you all so very much. And until next time, take care of yourself. Bye.